Okay, Bismillahirrahmanirrahim. Assalamualaikum and good day to all of you. So this recorded session, I'm going to cover on chapter 4, which is on the topic of oscilloscope. So this is the learning outcome for this topic. At the end of this chapter, you should be able to, number 1, describe how oscilloscopes work. Number 2, describe the difference between analog and digital oscilloscopes. Number 3, explain the basic construction of a CRT oscilloscope. CRT stands for cathode ray tube. And then number 4, understand basic oscilloscope controls. And finally, read and calculate the values from oscilloscope correctly. So let's dive into the content. So an analogy for an oscilloscope is similar to a camera. A camera captures images of objects. An oscilloscope captures images of electrical waveforms, in particular electrical voltage. So when we take a picture from a camera, we are interested in making sure that the images are clear, so that we can see all the objects or all the people in the photo clearly. Similarly, in an oscilloscope, we want to make sure that when we do the measurement, we can capture the images of an electrical signal clearly. So basically, an oscilloscope is a graph displaying device. So it measures the data, measures signal from an electrical source, and then it displays the features of the signal on a screen so that you can see. So the screen is somewhat similar to the one shown here. So we have the horizontal axis or the x-axis. This one will represent time. And then we have the vertical axis, which is the y-axis. This one will represent the voltage. And then we also have the z-axis. So z-axis we cannot see it because it's two-dimensional, but it will be represented in the form of intensity. Intensity means how bright the signal will be. So these are the common use of an oscilloscope, what it can measure. The oscilloscope can measure directly the AC and DC voltages, but it can also measure indirectly these elements here: the AC or DC current, the time of the signal, the phase relationship between two or more signals, the frequency, and also it can be used to perform evaluation of the signal in terms of its rise time, fall time, ringing, and overshoot. These terms we will see later on. So these are simple examples of electrical waveforms that are usually measured using an oscilloscope. So the most common one is the sine wave. We usually get this type of waveform when we measure output from our sockets or electrical power points. So we'll see sinusoidal waveforms such as this. If we measure the output from our normal PC monitors or PC systems, then for some of the components we will going to be seeing square waves when we measure. As for triangle wave, there are a few applications where we can see. One of the common one is when we measure parts of power electronic components in our car. Okay, some of the parts when we measure, we are going to observe a sawtooth wave or a triangular shaped wave. And then for a typical monitor like a high definition TV, when we measure the output, then we are going to see complex waveforms like the one shown here. So these are just examples of typical waveforms that you usually encounter. Now, we need to understand the difference between analog and digital oscilloscopes. So digital oscilloscopes, the most common one are called digital storage oscilloscopes because it stores the data before it displays the data on the screen. Okay, so let's focus on the left part of the diagram here. So when we want to measure a signal, if we use an analog oscilloscope, it's going to capture the signal and it's going to display the data directly on the screen in real time. So these are the steps. So it's straightforward. But for a digital oscilloscope, when we start the measuring process, it's going to go through an ADC. ADC stands for analog to digital converter. It's going to convert the analog signal from the probe here into binary form. So binary are basically ones and zeros. And then it's going to store this binary data in the oscilloscope and it's going to use it to regenerate the figure shown on the screen. So these are the steps. So it converts first the measured voltages into digital form. It acquires the waveform as a series of samples. It stores the samples until there is enough sample to describe a waveform, and the samples are reassembled for display on the screen. So these are the critical differences between the two. Now let's look at the advantages for each type of oscilloscope. So these are a very simplified comparison. So for analog, the three main advantages are the cost. Analog scopes are much cheaper if you compare to an equivalent but digital version. And then in terms of performance, in many applications, using analog oscilloscope is already sufficient. So you don't need to buy a more expensive scope if your measurement is just going to cover the typical types of measurement. So it's usually adequate for lab usage. For undergraduate level, typically analog oscilloscope is already sufficient. And then another advantage for analog is that it has intensity grading. That means because the data is displayed in real time, if the signal is strong, then it will be represented as a brighter beam on the screen of the oscilloscope. If the signal is a bit weaker, then the beam will be less brighter. So you can see directly whether the signal is strong or not from the intensity of the beam that you see on the screen. This is not available for digital oscilloscope. Of course, advanced digital oscilloscopes, they also have this ability, but I'm talking about a normal digital storage oscilloscopes. Okay, now we move on to the advantages of digital oscilloscopes. Now the most important or prominent advantage is high-end performance. Because the data is stored, okay, so before it is displayed, so you can analyze the data, you can do many things. You can save, you can print the figures, you can process the data. If your signal is complex, you want to process it, you can do so either from the microprocessor in the oscilloscope itself or by using an external computer if it requires more processing capacity. Okay, another advantage for digital oscilloscope is transient. It allows you to capture and view transient events. Now, transient event is the event that either occur in a very, very short time or it occurs only once, like a glitch or a sudden change that is not easily observed using analog oscilloscope. So because it samples the data, you can capture the transient effect. And because it is stored, the data is stored for digital oscilloscope, so the waveform can be displayed even when the signal disappears. When you measure, the signal suddenly disappears, you can still recreate the image from the sample that has been taken earlier. So these are a few of the comparison between the two. Now let's look at the basic construction of an analog oscilloscope, focusing on the cathode ray tube type or CRT. So this is a basic representation of CRT. So the whole component or the whole equipment itself, inside it is an evacuated glass tube. Basically, it's a vacuum glass tube inside this. All right, and then you have the components here, electron gun, and then you have the deflection plates, and you connect the input you want to measure. You are going to connect it to the vertical deflection plate, and it's going to determine the movement of the electron gun here. The electron gun will produce an electron beam, and the beam will be deflected by these plates depending on the type of input signal that you get, and it will be represented by the display screen here. When the beam hits the screen, it's going to be displayed according to the amount of deflection produced by the signal. So we are going to look into more details after this. So again, the horizontal axis is the time axis, the vertical axis is the voltage axis, and the plates here, the vertical and horizontal plates, is going to determine what is going to be displayed on this screen here. Okay, so for cathode ray tube, the screen is coated with a substance called phosphor, which is a fluorescent substance, which is supposed to display the electron beam. It's going to glow when an electron hits the surface. So that is why you can see the shape of the waveform. Okay, let's look at the components in more detail. So these are the list of the components. So first we have the electron gun. So the electron gun is going to produce a focused and accelerated electron beam. So it's going to produce a beam here, which is represented by the dashed lines here. And then we have the input. So inputs usually require the need to be amplified. So we have the vertical amplifier to enlarge the signal obtained from the input. Okay, and then it goes to a delay line. So the delay line is going to delay the signal for some short amount of time at the vertical section. So you see the arrow here. At the same time, when the input goes to the delay line, another signal will be also passed through the trigger circuit. Okay, so the trigger circuit, the function of the trigger circuit is to synchronize the pulses, create a pulse to synchronize the value that is obtained from the input with the value that is going to be generated by the time-based generator. Okay, the time-based generator is used to generate a sawtooth voltage, which is going to represent the time of the input signal. And then, of course, this generator also require an amplifier to enlarge the value of the signal, and it's going to be represented by the horizontal amplifier here, the horizontal deflection plate here. Okay, and then we have so I already explained this part. The trigger circuit is going to synchronize this value from the input and the time-based generator. And then we have the power supply. So the power supply consists of two parts or two power supplies. We have a high voltage negative power supply and low voltage positive power supply. So for the low voltage supply, the range is around 300 to 400 volts. And for the negative supply, the range is between negative 1000 to negative 1500 volts. And of course, we have the screen, which is coated with a fluorescent material, like what I told you just now. Now, let's look further into the electron gun. So here, you see the electron gun as like a small component, but actually inside the electron gun you have some more subcomponents which is represented here. So the cathode is the part where the beam is produced. Then it's going to pass through what we call as the control grid. So the control grid is going to determine the intensity of the beam, how strong the beam is going to be projected on the screen. So you have a dial or a knob on the oscilloscope panel that you can use to adjust this intensity. So it is connected to negative 1200 volts. And then after that, it's going to go to the first anode. The first anode, the function is to focus the electron beam. And we also have another dial or another knob you can adjust to control the focus. And then it's going to be passed through the second anode. And the second anode is going to be used to accelerate the electron beam, make it faster, make it hit the screen faster. So if it's hits the screen faster, then the display is going to be more clear. So the combination of the first and second anode produces an electric field that focuses the electron beam on the screen. So you see here that the negative high voltage supply is used for the electron gun. So we have negative 1200 in this example. So the voltage will become more towards positive. Once it reaches the second anode, the voltage is going to be around 0 or similar to ground voltage. And then the positive low voltage from 0 to 300 or 400 is going to be used to power all the other circuits in the oscilloscope. Okay, so the negative part is only for the electron gun. Now these are the advantages of using a negative high voltage supply. So number one, it protects the operator from high voltage electric shocks. Okay, and then number two, it minimizes the use of blocking or coupling capacitor. And then number three, because of the nature, the deflection voltages are measured with respect to ground, there is less insulation required between positioning controls and the cases because it's isolated. The negative power supply is only for the electron gun, so it's isolated. They require less insulation, so the cost of fabrication is much cheaper. Okay, now let's look at the deflection plates. So the input signal is going to be reflected on the vertical deflection plate. It will move the electron beam in the vertical direction, either up or down, depending on the type of signal. And then you have a time-based generator which will affect the horizontal plate, and it will sweep across the screen and display the electron beam on the horizontal axis, left and right. The delay line in the input signal is used to slightly delay the input so that it matches the output from the time-based generator. So the delay is very small, only around 80 nanoseconds, which is like 80 times 10 to the power of minus 9. Very, very short time. But the purpose is that so that all the signals that is captured from the input can be displayed on the time axis. Okay, again, there's a lot of technical details here. I'm not going to go into the technical part to explain how this happens because it's beyond the scope of our topic. Now let's look at the digital oscilloscope. Now the basic digital oscilloscopes consists of these elements here. So we have the amplifier to amplify or make the signal become larger. And then we have the analog to digital converter to convert the signal into binary form, like what I explained previously. We have a demultiplexer to route the input into the relevant digital output depending on what we want to display and what we want to process. We have the acquisition memory, which is going to store the data. We have the microprocessor which is going to process and analyze the data. And we have the display memory that is going to generate the waveform on the display. Okay, so this is a simplified explanation of a digital oscilloscope. Now, let's look at the control of an oscilloscope. So this is example of one oscilloscope. This oscilloscope has 4 channels. So you see here, channel 1 up to channel 4. That means you can connect up to 4 different signals in this oscilloscope. Okay, there are also 2 channel oscilloscopes, a bit cheaper, but you can only connect 2 signals to measure. Alright, and then there are 3 main sections labeled vertical, horizontal, and trigger. So you can see the items here. This one is horizontal. So remember, horizontal is to adjust the time. And then you have vertical. Vertical is to adjust the amplitude of the voltage. And then you have a trigger circuit. So these are the explanation for each part. So vertical is used to adjust the attenuation or amplification of the signal. So it is represented in volts per division, and we use it to control the amplitude of the signal, the height of the signal, how high or low we want the signal to be displayed. And then we have the horizontal axis to adjust the time. So we have second per division to set the amount of time per division represented on the screen. And then we have the trigger segment here. We use to stabilize a repeating signal or trigger a single event when we measure. And then to measure, we have probes. Okay, and probes are connected to the point we want to analyze. So a simple probe, we can have like a conductor, and we have a shielded core, we have some carbon resistance, and we connect the end part to the point we want to measure, and it's going to be connected to the oscilloscope input. Okay, so you can read about the details. The shielded core here, the core here is there to protect from measuring noise. When you want to measure a circuit, sometimes there are noise, so we want to protect it from capturing the noise signal. Okay, this one is very simple, one-to-one. That means it's going to display the signal directly as according to what is measured. So there is a slight problem, which is a slight reduction in the waveform amplitude and a slight change in the wave shape when we use one-to-one direct probes. So typically we use this one called 10-to-1 high impedance probe. Okay, so these are examples of probe I taken from one manual produced by Catronics. So these are common oscilloscope probes. We call it as passive probes. Now these 2 figures represent a specific application where you require customized probes. Like for example, if you want to measure a motherboard or an electrical circuit, so the components, the location is very small, so you require a very precise probe to measure. Like this one, the probe here, they want to measure the timing, the sequence of a microprocessor. So you can see that the probes here are made of gold, because gold is a good conductor and it's also not easy to be oxidized. Dia tak mudah berkarat. So that's why it's used for this application to check the clocking time of processors. Okay. So these are high impedance probes. High impedance probes is more commonly used for oscilloscope. So this is the configuration. To explain about how this configuration works, I encourage you to watch a video on YouTube, which I will also include in the ULearn section for week 7. And it has the explanation on how this works, what the circuit does, in a more interactive form. Much nicer for you to see rather than you watch from this lecture note. Okay, so anyway, so this is the configuration of the 10 to 1 probe. So you have a 9 mega ohm resistor here, and you have a 1 mega ohm resistor here. So 1 divide by 9 plus 1, so you get 1 over 10. So that's why you get here 10 to 1 high impedance probe. Okay, there are some electrical principles also involved. You have a capacitance here. This one is actual capacitance, this one is stray capacitance. Okay, I'm not going to cover what that is. And this one is adjustable capacitance, which we are going to adjust to compensate for our signal. This is the equation that is used if you want to calculate. And to know the practical application of C1, I encourage you to watch the video. So in the video, you'll see this waveform when the value of capacitor is correct, when the value of capacitor is too small, and the value of capacitor is too large. So we are going to adjust the value of the capacitor to get this perfect wave shape, square wave shape. So this is the title of the video, and the link is available in UTeM. Okay, what do we use oscilloscopes for? So we use it for waveform measurement. So here are some definitions: frequency, period. So 1 second. Here we have 3 complete cycles. So we say we have 3 cycles per second, and the frequency we call it as 3 Hertz. So 3 Hertz, basically we have 3 complete cycles in 1 second. Okay, so 1 period is defined by the range it takes, the time it takes to complete 1 complete cycle, 1 full cycle. So we call it as a period. For the voltage, I think you are already familiar with this. So if we have a voltage like this, so the amplitude refers to from 0 to the peak of the voltage, which is 1 volt, and the peak to peak is from the top to bottom. Okay, so remember this term, amplitude. And then we can also use it to measure phase shift. Like in this figure here, let's say you have voltage and current. So there is a phase difference between these two waveforms. And if you want to measure it, we can use oscilloscope. And these are the definition again for peak, peak to peak, and RMS voltage that we already studied in the AC meter chapter. Okay, so let's look at a simple example. This is voltage measurement, example 7.1. So the vertical attenuation is given as 0.5 volt per division. So here is called 1 division. So we have from here to here is 1.5 division. From here to here is 1.5. So total we have 3 division on the vertical axis. So to calculate, we simply multiply 0.5 volt per division with 3, which is the peak to peak distance. So we get 1.5 volt peak to peak. Now for the time it takes for a complete cycle, 1 complete cycle is 4 division. So 1, 2, 3, 4 for it to have a complete cycle. So 4 division, let's look at example 7.2. So if the time per division is set to 2 microsecond per division, that means one box there is 2 microsecond. So you multiply by 4, you get 8 microseconds. And to get the frequency, you simply divide 1 over the value of the period, 8 microsecond, to get a frequency of 125 kilohertz. Alright, now let's look at another example. This example is taken from an actual oscilloscope reading. So you see the labels here. So this one, we have a 2-channel oscilloscope, channel 1 and channel 2. So channel 1, the volt per division is 1 volt per division. So remember that channel the volt per division, that means it's going to refer to the vertical axis, the y axis. So every box here, from here to here, for channel 1 is going to be 1 volt. So channel 1, the color is yellow, so it refers to this figure here. So we have 1 volt, 2 volts, peak to peak. Okay, and then for channel 2, the volt per division is 200 millivolt. So if you measure, so if one complete division is 200, that means one part here is going to be 200 divided by 5, which is 40 millivolts. Okay, so you can measure for this channel 2 here, what is going to be the peak-to-peak voltage. So this one here, for channel 1, one division, complete division equal to 1 volt. But for this part here, it's only 200 millivolt. So you need to differentiate between the two. But the time for both waveform is the same. It's 400 microseconds. So the time per division refers to the horizontal axis or x-axis. That means if I take from here to here, it is equivalent to 400 microseconds. So if you want to know one part of it, then 400, one whole division, we can divide into 5, 2, 3, 4, 5. So 400 microseconds, we divide by 5. So each part here represents 80 microseconds. Okay, and the trigger level and so on refers to where we want to start to measure the data or measure the signal. All right. Let's look at this figure here. So we have two waveforms. So the yellow one is connected to channel 1. The green one is connected to channel 2. Both have 500 millivolt per division. That means one box here, from here to here, represents 500 millivolt. And 10 nanosecond per division for the time. That means from here to here, every division equals to 10 nanosecond. So if you want to measure the peak-to-peak of the signal, we use this equation here. So we know that each vertical division is equal to 500 millivolt. So we can calculate the number of division from here to here. If you calculate, use the center point, because the waveform is quite thick. You take around the center point. You see that the number of division from here to here is 3.5, and from here to here is another 3.5. So you get 7 division. Multiply by 500 millivolt per division, you get 3.5 volts. That is the peak-to-peak voltage for the yellow signal. And for the green signal, if you measure, you get the peak-to-peak value is 5.6. When you multiply, you get 2.8 volts. Now for the time, so you need to calculate the time for a complete cycle. So let's say for the yellow one, we start from here. We need to calculate the number of division until here, which is a complete cycle. So if you calculate, you see that number of division is going to be equal to 10. So you multiply by 10 nanosecond, you get that the total period is 0.1 microsecond, which is equivalent to a frequency of 10 megahertz. Okay. So this is another application of waveform measurement. We can use it to measure the phase shift between two signals. So this is the phase difference between the two signals given as a small t. And then the period, we give it as a capital T, and we can use the ratio to determine the angle theta. Multiply the ratio with 360 degrees. Right? We can also use it to conduct waveform evaluation. Okay. Particularly, we are interested in the rise time, fall time, and pass width. So rise time is the time it takes for a signal to starting from 10% of its rise up to 90%. So this is called the rise time. And the fall time is the opposite, from 90% until it goes down to 10% of the magnitude or the amplitude of the signal. And the pulse width is the length in time of the average pulse width at the center here. At the 50% level, okay, we measure what is the time. The time is called the pulse width. Okay, now let's look at a few more examples. Okay, so now we move on to the example. So for this question, it's similar to the question that you've seen earlier. So you have two waveforms here labeled A and B. So we have the time per division is set to 0.1 and the unit is millisecond. It's not so clear here, but this one here is the time division. The unit here is millisecond, and the unit here on the left hand side is microsecond. For the voltage per division, which is the vertical axis, the value given is 200 and the unit is millivolt. So that means one box represents in the vertical direction is equal to 200 millivolt, while one box in the horizontal direction represents 0.1 millisecond. So by calculating the number of division, both vertically and horizontally, we get the following answer. So you will find that the peak-to-peak voltage for waveform A, it has 6 division. So we multiply by 200 millivolt per division to get 1.2 volts. And for one complete cycle or one period, we go to the horizontal division, it's going to be 6 division. So we multiply by the time per division, and to get the frequency we need to have the inverse of the period, which is 1 divided by the result of this multiplication. So you get the frequency as 16.7 Hz. So we repeat the same process for waveform B to get value of 480 millivolts and the same frequency 16.70 Hz respectively. And the phase difference, since it is equivalent to 1 division, since 6 division is equal to 1 complete cycle, which is 360 degrees, so for 1 division is equivalent to 60 degrees. So that's how we calculate for this waveform. Now for another example, this one involves the rise time, fall time, amplitude and frequency. So remember, the amplitude we only measure from the x-axis up to the peak value. So the amplitude is given as 4 times 2 volt per division. So we can see here that the volt per division is 2 volts and the time division here is 5 microsecond. So the unit here is microsecond. And we get the frequency as 35.7 kilohertz. Now recall that the rise time is the time it takes for the waveform to rise from 10% up to 90%, which is here represented by delta V. This is the rise time, and consequently when it drops from 90% to 10%, that is the fall time. So basically delta V here represents both the rise time TR and the fall time TF. And by calculating the number of division here, we get the following results. The rise time is equal to 3 microsecond and the fall time is equal to 2 microsecond. So remember that for signals, you cannot assume that the rise time and the fall time is the same. So there may be some differences depending on the type of signal you are measuring. Next, so we have covered the fact that we can use oscilloscope to measure voltage. and to measure period, to measure frequency, and to measure phase difference. Now we can also use an interesting phenomena from the oscilloscope, which is called the LISSAJOUS pattern. We can use this pattern to determine two things: whether we want to determine a source with an unknown frequency, we want to know what the frequency is, or we want to measure the phase difference between two different signals, or two different the frequency should be the same. We are talking about the phase difference here, so slight typo here. So the unknown frequency is given to measure or to apply this LISSAJOUS pattern. So we connect the source with the unknown frequency to the vertical plate, and the known frequency, so the known frequency will act as a reference. We connect it to the horizontal plate. So we do some setting on the oscilloscope. We set it to external sweep and switch off the sync control, and then we are going to get some figures, and from the figure we can determine what is the frequency from the unknown source. Okay, so these are example of LISSAJOUS patterns that you may see on your oscilloscope, depending on the ratio between the vertical frequency and the horizontal frequency. So remember, the vertical is the frequency where we do not know, and the horizontal is the frequency that we know. So we are going to use this ratio to determine the frequency for the vertical connected input. So it can be in either horizontal or vertical. So you have two different types of figures here. This one is called the patterns for integral frequencies. So integral frequencies you are going to get when the ratio is either the top part of the fraction is 1 or the bottom part is 1. So here you see, if the frequency is equal, you're going to have a complete circle or a perfect circle. If the horizontal frequency, the known frequency, 2 times the known frequency is equal to the unknown frequency, then you'll get the shape of infinity here. And you are going to see the shapes here corresponding to the equations from A to I. Okay, these are called integral frequencies. So you're going to see the shapes here. And we have non-integral frequencies. When we get the ratio such as this one, we have 3/2, 2/3. We have neither of the either the top part or the bottom part, which is equivalent to 1. So we call that as non-integral frequencies. So we are going to have a slightly weird shape like this one. And we call this part here as you will see the next equation on the next slide. So if you are using integral frequencies, then we calculate the number of horizontal loops. And for non-integral frequencies, we are going to calculate the number of horizontal tangencies and corresponding vertical loops and vertical tangencies. So you see here, for an integral frequency, the shape is a loop. But for non-integral, the shape is slightly skewed. So we can say it as tangencies. We call it as tangencies. So this is a simple example. So we have two sine waves. If the signal applied to the horizontal input is twice the frequency of the vertical input. Okay, so if the horizontal is equal to twice the vertical. To sketch the LISSAJOUS waveform, so we get the following equation here: Fv equals to 1/2 Fh. And if we look at the LISSAJOUS pattern from the figure just now, this is what we are going to get. So the shape of the number 8, similar to a number 8. Now, just see this exercise. Read it carefully and then try to sketch the Lissajous waveform using the example given before. Okay, so another benefit of having Lissajous patterns is it can be used to do phase measurement. So oscilloscope can be set in the XY mode to determine the phase angle between two signals of the same frequency and amplitude. Okay, so this is the shape that you are going to see depending on the phase difference between the two signals or the two inputs. So let's say you have the following figure. You have an ellipse and this ellipse is tilted towards the right. So if we go back here, when it's tilted towards the right, is equivalent to figure A here, where the reactance and resistance is unbalanced, right? So in order to determine the phase angle, we can use this equation: sin theta is equal to y1 divided by y2, where y1 is the y-axis intercept, the point where this ellipse crosses the y-axis, and y2 is the maximum vertical deflection, which is the peak value here. So if we have the value as follows: y1 is equal to 1.8 cm and y2 equals to 2.3 cm, we can directly apply this equation to get the angle between these two signals is 51.5 degrees. Okay, so when we talk about phase difference, this is what we are measuring: the phase difference between the two signals, how far it is apart. So remember that we can only use this if the amplitude is the same and the frequency is the same. If any of it is different, then we cannot use it to do phase measurement. We cannot apply the Lissajous figures. So this is a guideline on the shapes, a more detailed guideline on the shapes that you're going to see depending on the type of phase difference. So for example, let me start here. If there is no phase difference, that means delta here del here equals to 0. That means, for example, the blue waveform and the green waveform overlaps each other. Then when you set the phase measurement, you're going to see a straight line, like a slanted line, like the one shown here. And as we go along in clockwise direction, so when the phase difference is 45 degrees, we are going to see this shape. When the phase difference is 90 degrees, we are going to see a full circle, a perfect circle, and similarly at 270 degrees or negative 270 degrees, you're going to see a full circle again, and in between you're going to see shapes like this. Okay, so when you see this kind of shapes, you already know in general what is the expected phase difference between the two signals. So this is just a full picture of the types of Lissajous patterns that you can see in the oscilloscope. So to understand better, I will also include in the ULearn week 7 another YouTube video on how you can generate Lissajous figures for phase measurement using an oscilloscope. Okay, so that's it for this topic. Thank you.